first thing I want to review then, laws of exponents. Not that these are necessarily curriculum that you haven't learned like this year, but I think you guys have learned this in the past. Quick review then. If I give you x to a to the b and e to the c, that might be like, say, x squared times x to the third. Oh my goodness, I can't write today. That's the same thing as x to the 5. Do you guys remember that rule at some point in your life? And then another rule is divided by. If I gave you, like, say, a to the 5, or x to the 5, divided by x to the 3, it would be equal to the x to the 2, because you're going to subtract them. And then one more rule, if I gave you x to the 3, and I asked you to square it, really that means you have x to the 3 next to x to the 3. So therefore you have x to the 6. Because you're really timesing the 2 by the 3. Those familiar? Okay, well, long story short, if there's rules for exponents, there's also rules for logarithms. Okay. And here are some of those rules for logarithms. They're all in your data sheet. My goal today is to show you how these rules work. These are the product, quotient, and power rules. Okay. So I just want to show you how they work. This guy right here is if you have it's probably better to start with this side here. If I give you log of 3, and I ask you to add log of 2, just like with exponents, adding and multiplying are kind of similar with exponents. Well, this is actually the same thing as log of 6. Type in your calculator just to confirm. So type in log 6, find what it is in the decimal number. Well, go with base 10, just to be consistent. So like type in log 6, get a decimal number. Then type in log 2 and add log 3, and they should be the same. Okay. So the reason why is that logarithms and exponents are similar to each other. Back here, if you multiply is similar to adding, in a way. Well, it's just backwards here. Here, if you multiply, it's similar to adding, that's all. Type in log 6, get a decimal number. Okay. Well, what numbers could times to give 6? Well, 3 and 2 could times to give 6. So if you were to take log 3 and add log 2, it should be the same as whatever log 6 was. Let's try a few more examples. Maybe I'm not making my point very well yet. Bear with me, sorry. Give me a number.
2.
Perfect. I have 7 and 2. I'm going to do log of 7, and I'm going to do log of 2. So I'm going to add these two numbers. So this is apparently equal to 1.146. What other log should this be equal to? Log of 14, yeah. According to this rule that I'm trying to show you here, if you have two individual logs that are added, it's the same thing as timesing them and going whatever 7 times 2 is. Collectively, they should be the same. Let me try one more. Give me 2 more random numbers and
3.
something very large. 5 and
28.
maybe a little less than that.
23.
5 and 23. Okay. So if we do log of 5 and we add the log of 23, I get this value. Okay. Okay, 5 times 23 is 115. So if I also do the log of 115, it should also be equal to 2.06, which is.
Do we need to know why?
Would it suffice to say that logarithms and exponents are very similar to each other? So if this rule made sense back here, the idea of timesing equals adding, would it also make sense then that timesing equals adding? Would that work for now? I can show you a maybe more complicated proof later, but so long as you understand how it works, like that it works, and a bit of why it works. Okay, similar concept then. Back here, if we have two things that are divided by each other, it's the same as subtracting them. So applying that to logarithms, if you can divide two numbers by each other, it's the same thing as subtracting them. So let's test some numbers here that we can actually divide though. So like let's say this was 20 and 4. So I go back to this guy here, throw this together. So 20 divided by 4 would be 5. So here's log of 5. Okay. It should be the same as log of 20 then, minus the log of 4. Right, so this 20 divided by this 4 is log 5, and hopefully you can prove the same thing. So this 20 right here, if you were to divide it by 4, you'd get 5. So if you also did just log 5, they'd be the same as each other. Subtracting is similar to dividing. Give me 2 more numbers. Let's say they don't actually divide. Give me 2 numbers.
7 and 17.
7 and 5. Okay. Let's try the log of 7 minus the log of 5. Okay. This should be the same as the log of whatever 7 divided by 5 is, which is not an even number, but that's fine. We can still work with it. So log of 7 minus log of 5 is the same as a single log of 7 over 5. That make sense? Okay. So, long story short, that is a rule for quotient and product for logarithms. And in some cases, you might find that to be useful in solving the question. And I'll give you some examples in a bit. There's a few more rules I need you to know, but let's work with that one for a bit here. So first question, if I say gave you log 15, could you write this as the sum of 2 logs? Sure, that's one way of doing it. This could be log of 5 plus log 3. Is that the only way of doing it?
15 is 1.
Sure, you could do the log of 15 plus the log of 1.
Could you do decimals?
Why not?
7.5.
You could do the log of 7.5 and the log of 2. I mean, if you want to, type them in your calculator to confirm, but hopefully at a certain point you'll agree that this rule is consistent.
So, how the log of 15, so if you take the same log of 15 and then you're adding more to it. So.
Try this. What is the log of 1? Put it in your calculator. Log of 1 is actually 0. So that's the only reason why that would work, because I'd agree. It seems like you should be adding more, but you're actually adding nothing in that one example. Raj.
4.
Okay. Nicole? You're good? Okay, so going back to logarithm though, a log is our way of rearranging an exponent, right? So if I gave you log base 2 of 3 equals x, it's our way of trying to rearrange 2 to the x equals 3. So really a log is like a way of trying to rearrange an exponent, basically. But like in this example right here, it's just a number now, basically. Right? Like log of 5 is just some random number.
Log term is the inverse of exponential, right?
Yeah.
Okay.
So let me try another one here. Write log 6 is a difference of 2 logs. Okay, so like write log 6 as like say this, log 12 minus log 2. Does that make sense? That's one way of doing it. Because 12 divided by 2 is 6.
Oh, but that's subtracting before.
Subtracting means difference.
But 12 divided by 2, 12 times 2 is 6.
But subtracting, in terms of logarithms, means dividing. Like add and multiply are similar to each other, as divide and subtract are.
Okay.
So like here's another set then. You could do log 18 divided by log 3. Because 18 divided by 3 would be 6. So go backwards here then. Log 3 plus log 4 would be equal to log 12. Yeah. Can we extrapolate this to like more challenging things, like 3 of them? Sure, you just multiply everything. So 4 times 2 would give you 8. Times 3 would give you...
Yeah, you can do the base thing. Well, yeah, is the base effective?
Okay, so the base does stay the same then.
Okay. As
long as they're the same.
Yeah,
right?
as long as this base and this base and this base are the same, it'll work.
What happens if they're not?
Then they don't go together.
So can you have
It would be like trying to add this cube root of 7 to the square root of 1. Like they don't go together because they're of like different types.
Would you give us a question like that over?
If I did, you could not put them together, and the answer would just have to stay that way. Like, let me give you an example here. If I did ask you that, it might look like this. What is log 3 of 2 plus log 2 of 3? And your answer would be this. You can't actually put that together because they have different bases.
So you can't just like plug in your calculator and get that.
Well, okay, you could get me a decimal number.
But you don't want that.
No, I mean, unless that was one of the 4F, like it was multiple choice, like A, B, C, D, then the decimal answer could be there. But you can't actually like physically combine them. Kayla,
Are you recording this one?
I am.
Oh, good. Oopsie.
Okay, so what about this next guy then? Log 20 plus log 3 divided by log 15.
Would you go 20 times 3 divided by 15?
Consider it multiplying.
So a couple of thoughts here. I'm hearing bed mass is a good idea. We should multiply the 20 and the 3, but then divide by the 15. So 20 times 3 would be 60. Divided by 15 would be... Okay, take your calculators then. Confirm this.
Please
Type
repeat the
all of this
instructions.
into your
It's last
calculator.
call for anybody needing
Type this in
repaint.
your calculator.
If you do not
It
have,
should be the same
if
according
you didn't have a
to...
picture done, now is the time. You have 5 minutes
Because
to get
that's what
down to the
20
drum room,
times 3
and the
divided by
photographer
15.
will be gone.
Does that suffice to explain why it works? Like, I know it's not a very like confusing proof, but like enough repetition is one way of proving it. And then the other best way I have to explain it is going back at exponents and saying, well, like back here, it was pretty intuitive that you could take 2 to the 3, 2 to the x to the 2, x to the 3, and add them, right? And here you subtracted them. So it's similar properties because exponents and logs work together.
Yeah, yeah, I see now.
Okay.
So would that just be 32 then? 384 divided by 12.
Oh, okay, yeah. So you guys are one step ahead of me then. For this last one here, then you got to do whatever 384 divided by 12 is, which is 32. One more thing though. The next thing I might need to ask you to figure out is, could you evaluate this thing? Meaning, I want to actually have its number, like its like decimal value number. Okay. Okay. Most of you guys, I think I've shown you this at some point, depending on which calculators you have. If you have a TI-84 plus calculator, it is actually possible to type in a base, apparently. I didn't know this because my calculator doesn't do this. But let me show you in case you don't know. If you want to type in a special log, if you go to the catalog and then scroll down into the L's, some calculators let you do a log with like a special base. Most of you have those calculators? Except for like a few. Okay, if you don't have one of those calculators, there is another rule I need to show you here, which is on the next slide here. It's called the change of base rule. Okay. And I'm just going to go back to this one right here. It's this rule right here. Okay. Let's say you have a base right here and a number afterwards here. It is equivalent to doing the log of the big number divide by the log of the little number. So here's how you type that in then. If you can type this in your calculator, those of you who have that calculator, what was this guy's answer? 5. 5? Okay. This could also be written like this then. Give me the log of 32, that's the large number, and divide it by the log of 2. And that should also equal 5. If you want to test that. That's called the change of base rule. So for anyone who doesn't have a calculator that can type this in your calculator, this is the trick. If your base is not 10, divide by the log of the base. It might actually be easier than actually going to your calculator and finding that special log every time, because then you have to search for the catalog. So like, quick review here. If I gave you log base 10 of 10, this would be equal to log 10 for this 10, divided by log 10 for that 10.
Isn't the default log 10 anyway?
It is anyways, but it wouldn't matter. Type log 10 in your calculator then.
It's 1.
1, by 1 equals 1.
But isn't log 10 divided by log 10, isn't anything divided by itself going to equal 1 anyways?
Yeah.
So if you wanted to figure out what this guy was in decimal value, or scare Carla to death, dropping your calculator.
So just log 2 divided by log 3?
Other way around it, it's log of the big number
Oh, okay.
divide by the log of the base.
That's just gonna be really bad.
It's like 1.58.
Okay. I need to show you guys something that's a common mistake. This is not true. Log of 3 divided by log of 2 is not the same as log of 3 over 2, though. Because log of 3 over 2 is log 3 minus log 2. You can't get these two rules confused. That's probably the most common mistake, is that if you divide two logs like this, it's not equal to log of 3 over 2 collectively, because this guy right here is when you're subtracting them. So try not to get those confused.
But I have like a question, because wouldn't the logs technically cancel themselves out?
Okay, a log is not a variable. A log is like an operation. Yeah, because it would be like doing, like, say, the sine of 30 over the sine of 20. You can't just cancel the signs. Or it would be like saying 2 to the x divided by 3 to the x. You can't just cancel the x's and say, sure, it's just 2 over 3. Does that make sense? So logarithms as like a symbol are not like a variable that can be like canceled like that in that sort of way. Okay. I've got one more rule I need to show you. Let me go back to that first slide here. By the way, you guys, did I mention that all these are on your data sheet?
Yeah, that one good.
Oh, you should get a data sheet. That would help.
What's that on log B, C, log 8?
Okay, this is the last rule here. This guy right here basically says if you have a base and you have something, and the something itself has its own exponent, what you can do is take that exponent and put it in front of everything, and that's equivalent. Let me show you that in a few examples. Okay. First of all, does this guy right here, does it actually have an exponent? Well, what if I wrote it like this? What if I wrote it as log base 3, and rather than calling it 9, I called it 3 squared? Now does it have an exponent? Okay. So what the rule then says is that if you then have an exponent inside a logarithm, you can take that exponent and times it in front, which would be equal to 2 log base 3 of 3.
Is it like multiplied by everything?
2 multiplied by everything.
Okay.
Now, but what did I just show you about change of base? Log base 3 of 3 really means you have log of the big 3 divided by the log of the little 3. I don't actually care what log 3 is as a number. That's irrelevant. If I have the same thing top and bottom, it would cancel. So this answer should be 2. So if you have a calculator that can do different bases, try that. Or try doing log 9 divided by log 3. Long story short, it should be equal to 2.
So why can we go log 3 over log 3 on the last one?
This is that change of base one that I just showed a second ago, which is that it's log of the big 3 divided by the log of the little 3, as a way of trying to, like, if it's not a base of 10, this is how you can solve it. Like, let's say I give you log.
It's the same thing. Oh,
If I give you log base 2 of 3, it's log 3 over log 2.
Okay.
Okay, but this one is log base 3, which means it's log 3 over log 3. I don't actually care what log 3 is as a number. That's irrelevant to me, because I have the same thing top and bottom, so I can cancel it.
Okay.
And that's why the answer is 2. And I proved that like 3 different ways. Now, you could bring the 2 down in front and do some stuff here. You could just type this in your calculator. That should also equal 2. Or if your calculator is capable of it, you could just type this guy in your calculator. The reason why this one is the most important is usually for square roots, though, and cube roots. So for this guy right here, do you guys remember how to write a square root as an exponent?
Yes.
What's the exponent of a square root?
Negative.
No.
One.
1/2.
Oh, yeah.
If I give you the square root of x, do you guys recall this from last year? It's equal to 1/2.
Oh.
Yeah.
And if I give you the cube root of x, it would be equal to 1/3. This is where it comes up most then. This would then be equal to log base 3 of 27, but I have a square root here, so that's 27 to the 1/2. Okay, I mean that is an option, but here's another way then. Take the 1/2, bring it down in front, so you have 1/2 of log 27 with a base of 3. And then if you can't figure this out in your calculator, you could just go log 27 divided by log 3, find what those two things are, and then times it by 1/2.
Couldn't you break 27 down into a...
Sure, you could even break 27 down into 3 to the 3 if that helped you.
Then
Would you
take
put
the
the
3 and add it to the back?
Sure, I would times by it then. So you could say this guy is 3 to the 3 over log 3. You could pull the 3 down in front, which would give you 3 times 1/2 times log 3 over 3, which those would cancel and you'd have a 1.5, 3 over 2.
Is there a square root sign in there?
Yeah, there's a square root sign right here. And this guy right here, I'm meaning to be a 4th root, by the way.
So that'd just be 27 to the power of 1/4.
Yeah. Make some room here then. So for the last example here, if I give you log base 3 of the 4th root of 27, it could be log... Now, what you may want to do is just start dividing by log 3 right off the bat. Like, call this log 27 to the 1/4, divide by log 3, because the dividing by log 3 part takes care of the base not being 10. And then this 1 over 4 just has to come down in front then. So you'd have 1 over 4 of whatever log 27 divided by log 3 is. And I could put that in my calculator.
So could we just leave it as log 27 to the 1/4 divided by log 3?
Sure, if you want to type that in your calculator, that would work as well. The key now, though, is when I give you a question, sometimes those rules can be useful in solving a question. Because I want to go back to that multiple choice question I started class with, that you probably were looking at going, I don't know how to solve it. Now there might be some ways that you could solve that question. So let me just go back here. Let's try this one again now. Now that I've given you guys a few more skills, anything come to mind? Okay, so ignore the 4 answers. We'll probably don't get distracted by looking at them just yet. Using the rules that we have, do I have any exponents?
Yes. Wait, no. We have variable.
Well, I could, if I wanted to. Could I write it like this? Log base 3 of 3 to the 3 with an A? Okay, now before I bring the 3 to the front, though, I also have things that are times by each other. What's the rule for things that are times by each other?
Multiply them.
Add them. So then what I could do is then I could separate these guys by making it log base 3 of 3 to the 3 plus log base 3 of A. I lose you guys on that step?
I just
Okay. Do you see how like the 3 to the 3 is timesing by A? Well, one of the rules I showed you to start class was if you ever have things that are multiplied, it's the same as adding. So I could take log base 3 of 3 to the 3 and add it to log base 3 of A and separate it into 2 different additions. Okay, one of the rules I showed you here, Laramie, if I have log 2 plus log 3, it would be equal to log 6.
Yeah, I got that.
Okay, well now I do it with letters here. If I have log base 27 plus log 3a, that would be equal to log 3 27a. And what I'm doing is I'm taking this guy right here, which are multiplied here, and I'm pulling him apart into two different logs. I'm then taking this 27 and making it into an exponent, because Conlon, I think, pointed out to me that this 27 here actually has an exponent to it. So if I then take that exponent and I drop it down in front, make some more room here. So then you'd have 3 log 3 over log 3. And this guy would be log 9 over log 3. Well, this guy right here is what happens when you have the same base? It always cancels.
9, isn't that 8?
And then couldn't this guy right here, couldn't I actually find in my calculator what log 9 divided by log 3 was?
Where's log 9? Is it A?
Oh, sorry, A. Sorry. I thought that was a 9. Sorry. So ignore that. Then the answer is A is what you're saying here. Sorry. I thought that was a 9 because I was thinking 9 over 3, I can actually put that in my calculator.
Okay, so 3 plus log.
Sorry, I screwed that up.
It was 3 times log 3 plus.
Okay, maybe I should try this one more time from the top because I screwed that up.
All of those.
Sorry, guys.
I was really worried about that 9. Where did that come
Okay,
from?
let me try this one more time. Maybe this makes more sense here. Before I make 27 into 3 to the 3, could I split it up into log 327, log 3a? So that's using the rule where things that multiply are the same as adding. Make sense? Well, what you could do here then is you could, if you wanted to, type in your calculator log 27 divided by log 3. That would work. Or you could say, well, log 27 is really 3 to the 3. You could drop the 3 down in front and say you have 3 log base 3 of 3's, which is going to cancel anyways.
If we were like, oh well, log 327, just do that.
You could do that.
But that wouldn't help us in this question because...
Well, it would have actually, because if you do like log 27 divided by log 3, that should equal 3 in your calculator if you do that.
Okay.
So that could have worked. That could have been faster.
Okay.
And then this last guy right here, I guess I couldn't do anything to it, so it was always going to add to that.
Why is it? Oh, sorry.
Let me ask Kayla's question first. She's been patient.
If our logs have the same bases, does it just stay the same?
Yeah. So like this base right here of 3 needs to be here and here according to our rules.
Okay. When you're multiplying them together, it wouldn't make it a log 9.
No. Because that's like saying, how do I put this? If we had 2 to the 4 times 2 to the 3, the answer is going to be 2 to the 7, not 4 to the 7.
Okay.
That makes sense? Because this is where exponents and logarithms come back together again. This and this are very much allowed to add, but the base of 2 and the base of 2 must stay the same. Therefore, if you're going to have the log base 2 of 4 times 3, like this, then it can be the log base 2 of 4 plus the log base 2 of 3. So things that multiply could also, if it helps you, be added.
But can't things that add up to also be multiplied?
Well, you could like you could take this guy and bring it back to here if you wanted. So you could then say it's log base 2 of 12. That would work. Or you could say log of 12 divided by log of 2 if that helps. That's also true.
Can you back up to the question to that? Yeah.
Here.
Is that where you got the log 3 over log 3 up?
Right, okay, so here,
When you divide, do log 3 though.
okay, so here the 3 had come down in front, so that's a completely different 3.
Yeah.
This right here, log base 3 of 3, the change of base rule means do the log of the big number divide by the log of the little number.
So it's the same. I mean, they cancel.
They're for sure they're gonna cancel. Like if I gave you log base x of x, I guarantee you that's equal to 1. Because you're gonna end up with log of the big X over the log of the little x. I don't even need to know what x is. but I guarantee you it's going to cancel. Does that make sense? Raj?
How did you solve for A?
We didn't. That's the thing, is the goal of this question was not to solve for A.
Yeah.
It was just to rearrange it. And that's what made this question tougher than these ones here. Here I wanted you to actually solve for A or solve for X.
How would you solve for A?
Well, you can't because it's not equal to anything. Does that make sense? And this is where they'll try to throw in a challenging question. You can't even type this really into your calculator because there's no equal sign. Does that make sense? Like, we don't know what it's equals to. So how do you even put it in your calculator?
Could you, like, say substitute A for...
You need to know 4 rules, basically. First rule, numbers that are multiplied, you can add them. Numbers that are divided, you can subtract them. If you have an exponent, you can pull the exponent down in front. And if the base is not 10, then just divide by the log of that base. So like if it's log base 2 with 3, just divide by log, like, I should write that out. Yeah, if I give you log base 2, 3, then you can just say log 3 over log 2. Those are your 4 rules. I'd say they're probably fairly simple to work with when I give you numbers. They're not going to always give you numbers. They're going to often give you letters. Okay, so I want to try to throw at you some more challenging questions. Oh, that's not an eraser. I just made it worse. Okay, so first one here. We have 2 logs being added. What could we do to them? Okay, so you'd have just a single log. I'm going to put a large bracket around it here. Heather, could you grab the door? And we need to multiply these guys. Good, because chances are they'd want you to actually FOIL it and get you log of a squared minus b squared.
That's it.
That's all that one would be. Okay, so glad it wasn't that bad.
Time out, and that's it. Like, you don't. I guess there's no equal, so you can't solve.
Yeah, that's the thing, is when we give you questions like this, it's not like there's an equal sign that we're trying to solve, we're just trying to simplify things. So let's try this next guy here. First, we've got some stuff that's being subtracted and then added, but I've got a few other twists in here. There's a 3 here, and this guy's got a 5th root. Okay, so first let's talk about this 3. We don't normally want that 3 sitting there. Well, we could divide it out, but there's no equal sign to divide it to the other side for it. Make it the exponent. You could take this 3 and make it the exponent of b to the 3rd.
Oh, goodness.
That makes sense? Good. That's the other thing you could do. This c that's 5th rooted, you can make that 1/5.
So can we just leave it as C then?
Ah, good, because that's the other trick here, is there's also that 5 up front, and the 5 would also have to come up. But if you have a 5 and a 1/5, wouldn't they just cancel each other?
Where are you getting your 5th root from?
Okay, let me go through that one a bit closer here then.
The square root of 5.
Okay, some of you guys get this. So you've got 5 log 5th root of c. Okay. So the c could be written to the 1/5, because that's what a 5th root means. Give me one sec. Okay. But then this 5, just like the 3 can get brought up top, if you bring this 5 up top, then you'd have log c of 5 times a 5th. What is 5 times a 5th, though? 1. So really, all of that stuff cancels. All of this right here just simplified to log c. Colin, do you still have your question?
Yeah, if there's no base, is it just 10?
It's just 10 then. Yeah. So let me simplify this a couple of ways then. Just erase all this here. Just gonna save more room here. So log A, I'm not really gonna do anything to. Log B, though, is now going to have the power of 3 to it, because I brought the 3 up top. And this log C right here was supposed to be 1/5, but the 5 just made it regular log C. So now the question is, can I actually put these guys together?
Log A divided by B.
Okay, so what does subtract mean? Okay, so then you'd say it's log of A over B cubed.
Oh, I see what you're doing.
Okay, well that's my next question is, well, how do I do it with the C? That's a plus C.
Multiply A over B.
Multiply by
C.
C. So the A will divide by the B to the third,
Should we just leave it like that?
and then when we're done, we'll multiply it by C. We could leave it like that. A few ways that this could be written then. You could write this as log of AC over B to the 3. Well, here's why I want to show you some of these tricks though. If it's multiple choice, they might not write this as one of the answers. They also might write it like this. Log of AC B negative 3.
Oh, because of the. That is like a bad phrase.
So
Too many options.
B3 on the bottom means that it also could be written as a negative exponent. So A is on top, C is also on top because it's multiplied, but B, which was divided, I could put that on top if I give it a negative 3 exponent. All three of these are true. I don't know which one will be the multiple choice answer they give you though. They don't have to have common denominators, but they do have to have common bases. But the base of this log was 10, so is that one, so is that one. But in order to multiply, they don't have to have common denominators, like in here. Weird in terms of how its setup is. They're going to say, what if x was equal to log base 4 of 5, and y was log base 4 of 3? Now, right off the bat, you might think, well, hey, I can find what x is. X is whatever log 5 divided by log 4 is. So if anyone has a calculator, could you tell me what x is equal to?
1.160.
Sure. And then y would be log of 3 divided by log of 4, whatever that is.
1.79?
Okay. Here's the problem then.
Wait, what'd you get?
That was 2.
How does that help me? What'd you get?
I got 0.79.
Oh,
I don't know.
whatever. So I guess my first point is you could find what x is equal to as some random decimal number, and you can find what y is equal to as some random decimal number. The question is, this guy right here is also equal to some random decimal number, but how do I break that up into x and y? Like, how much of it should be this guy, and how much should be this guy? Right. We could do that. I've got a couple of suggestions here.
Yeah.
I know, that's the first challenge is like this question, what is it even asking? So let me start with this right here. This is what it's looking for me to work with, and I want to express it in terms of x's and y's. Okay. Now, log base 4 of 225, I could actually figure out some of the factors of 225. Okay. You guys remember doing factor trees way back in the day?
Yeah.
What does 225 break up into?
25 and
25 and what?
4, 8, and 9.
9? Okay, and then 25 would break up into 5 and 5. And 9 breaks up into 3 and 3. That make sense so far? So, would it make sense then if I said 225 was really 5, 5, 3, 3? Well, using our log rules then, we have 4 numbers that are all times by each other. So we could go log base 4 of 5 plus log base 4 of 5 plus log base 4 of 3 plus log base 4 of 3.
So,
Isn't that, wouldn't that be 2x same as 5 squared? 3? No.
Okay, so a couple of things here. I think some of you are seeing where we go next. Log base 4 of 5, though, is what x is.
Oh,
So that's an x. And that's an x. So how many x's do we have total?
2x.
Okay. And then this guy right here is a y. And this guy right here is a y. So you also have 2y. And so this is what the answer was.
That is.
Which, for those kids who probably wrote that diploma the first time, was probably like a... Because, like, without being shown how to do that one time, that's confusing.
I would have never thought that's what it was.
But
Like,
that's for help.
So like you have a certain amount of x's and a certain amount of y's that equal log 4 225.
Well, now if we want to test that, remember how I said we were finding this guy as a decimal number and this guy as a decimal number? If you were to take 2 and times it by that first decimal number, and then add 2 and times it by that second decimal number, it should be the same as whatever log 225 divided by log 4 is. Not that that was useful in solving it in the first place, but it checks your work for you.
so you do like 2 times log 4
Yeah,
Could
so
you
like
just plug that, reverse it back.
2 times log 5 over log 4, whatever that was. And then add 2 times log 3 over log 4. And if you did that, you should get whatever log 225 divided by log 4 is. That being said, that was really only useful for checking your work. For actually solving the question right off the bat, I don't think that was as helpful for.
No.
You could just use like multiple choice and play with that.
I don't know. That's tricky. It is doable, you're right. But like, this is the kind of question that they always throw like 1 or 2 of them on the diploma. And I can't prepare you for all of them. Because like I have no idea how they're going to phrase it. Like this was very, very weird phrasing.
I guess a lot of kids got it wrong.
Well, yeah. But they always throw a couple of those on there, right? And those are the questions that like separate the kids who get like, you know, like 95% and 100%. Like the really, really tough questions. Did that make sense after I showed you? Please don't feel bad that you didn't get it before I showed you.
Okay.
Because those are the kind of things where sometimes I just need to give you a few examples. Okay. I'm running out of time. Let me go right to my last example here. I want to go to this guy here. Okay. This is another typical diploma type question. Okay. I'm now going to ask you to find me the domain and range of this graph. Now, what you could do is you could type this in your calculator. But if you haven't figured this out by now, your calculator probably will give you some weird looking graph, and it's going to be hard to fully interpret. So it may be better to use some logarithm laws right off the bat. These 2 logs are being subtracted. What does that mean?
Divided.
Okay, so let's do that first. Y now equals log base 5 of the 2x minus 2 over the x squared plus 2x minus 3.
Oh, wait, in factor.
Good. Next step. I can factor. Okay, so if I factor the top, I'd have 2 bracket x minus 1. When I factor the bottom, I'd have 2. No, not 2.
No, just x.
X, subtract 1x plus
Should be 2 the middle cancel.
Okay, so
Ooh, there's a whole graph.
good. That's the first thing I wanted you to notice here, is that I've now made you combine a couple of things you've done in polynomial functions. We've done the logarithmic function in conjunction with the rational function, and by canceling this guy right here, you've now proven that it's log base 5 of 2 over x plus 3. But Heather made a note here. There is a hole in the graph where x is 1. Does that make sense? Okay. But if there's a hole in the graph where x is 1, that also means that y can't be a certain value either. So how do I figure out what y can't be? Okay, so just a little side note here. Take this equation and let's actually try plugging 1 in. So 2 over 1 plus 3 means I need whatever log base 5 of 2 over 4 is. You have a calculator, so hopefully you can calculate that. So like log of 0.5 divided by log of 5.
It's like negative 0.443.
Sure. So that's what y can't be. It can't be negative 0.4306 apparently. Okay, so that takes care of the hole in the graph.
Maybe.
Well, there's also an asymptote too that I should consider. Okay, so as I add to this, you also can't have x become -3. Okay. Now I'm going to recommend, now let's take a look and see what this graph looks like, because it could be really weird.
Just put
The graph I'm going to plug in, I think I'm going to keep it simple. I'm going to plug in this guy right here, and I'll just divide by log 5 to make it work. So I'll go log of 2 over bracket x plus 3. And then I'll divide by log 5 to make that work. This will be the graph that I try to sketch. So I'm trying to graph just this guy right here. And just in order to type it in properly, I'm doing log of 2 over x plus 3, which is this guy, and then I'm dividing by log 5, because my calculator can't do the whole put 5 as an actual base.
So could you have done like the second equation
Sure.
that we came up with there?
That one would have worked too if you wanted to.
And the one below that?
Sure, they would all have worked. Okay.
how many guesses?
Because here's what this graph looks like. Okay. Let's look at my table of values. Table set. Let's start at 0, and I'll go up by 1s. Let's look at our x values. I have x values at 0, 1, 2, 3, 4, 5, 6. So it looks like x can be positive numbers. X can even be -1. Could be -2, -3. It can't be though. Why can't it be -3? Okay. -4? Apparently it stops there. -5, -6, -7. So it would appear to me, looking at my graph here, that there's an asymptote right here going straight up and down at -3. So how would I then write my domain and range? Well, I'd say x has to be greater than -3. Was it actually allowed to equal -3 though? Okay. There's also one more hole in the graph though, x. And x also couldn't be 1. And then for my y values, there's an asymptote right here that should go straight up and down. So pretty much every y value should count right here. And this graph is slowly but surely going downwards. Is it going to keep going downwards? Yes. Is it going to get there very quickly? No, but it is going downwards. But there is one y value that we can't have. The one y value that we can't have was that -0.4306. So there's our domain and range.
Why just can't equal and then
Because that's the one hole in the graph that it couldn't be.
Yeah, but how can it be
This is like
greater than that if there's an endpoint?
It's not
There isn't an endpoint though. Your calculator just does not like handle drawing this line straight up and down very well. But this graph does have an asymptote drawing straight down right here and then going over like that. And that's where your calculator, you can't put your complete faith in your calculator because it may not draw asymptotes particularly well.
Does that y value or that x value keep on going?
Like these x's should keep going that way for forever. I don't see why they
But
stop.
do they get lower? And
They are getting lower and lower and lower. Like they're taking their time, but they will get lower and lower.